Hi everyone, welcome to discussion section 1. As always, my name is Andrea, and today we're going to be doing a walkthrough that covers state spaces as well as informed search. So to start out, let's think a little bit about state spaces by using this famous problem in computer science called the Towers of Hanoi. And in this problem, as you can see, there are these 3 pegs that we have, and we also have n disks that are stacked on top of these pegs. And these disks are of varying sizes. And the goal is to move these disks from one peg to the other until all of the disks are moved to the rightmost peg in exactly the same order. So in this case, it would be this increasing stack of disks where they get smaller and smaller the higher up you stack them. So that's kind of our goal here. And the first question we're posed here in the discussion section with is we want to propose a state space representation for this problem. Now, whenever I think about state spaces, I always think about what's the minimal quantity of information I need to keep track of in order to run a search algorithm or in order to understand the state of my game and what action I should take next to achieve my goal. And when I look at this particular problem, I notice immediately that the things that I should care about when I'm trying to win this game are the disks. So let's label these disks 1, 2, 3, 4, where the numbers are going to correspond to the size of this disk. And the other thing I'm going to care about is which of these pegs are the disks currently on. So here I know that there's peg 1, there's peg 2, and there's peg 3. And when I think about this representation of keeping track of all the disks and keeping track of all the pegs is almost good enough, but there's one other important thing I need to keep track of. And the way to think about this is think about potentially what we might want to check as a condition for whether or not we have finished the game. And in this problem, as I said earlier, the condition for finishing the game is to have all of the pegs exactly in this order on all the disks exactly in this order on the final third peg. And so that means that I can't just keep track of peg 1, peg 2, peg 3, and where all of the, and just like all the disks, I need to actually take care of the ordering. I need to know how these disks are ordered on each peg in order to understand whether or not we have met that criteria of having all of the disks ordered correctly on the final peg. And so with that in mind, I'm going to propose a state space representation that's going to essentially keep an ordered list of disks per peg. So for example, for peg number 1, right now we have this list 1, 2, 3, 4, where each of these numbers correspond to which of the disks are where on that peg. For peg 2, we have no disks on them right now. And for peg 3, we also have no disks on them. And so all I need to do is keep track of these 3 lists, 1 for peg 1, 1 for peg 2, 1 for peg 3, which are ordered according to where each of the disks are on a particular peg. What's the size of the state space? Well, let's think about this. In our problem, we have these n disks, in this case, n equals 4. So let's write down each of these disk IDs, 1, 2, 3, 4, all the way up to n. When I think about each of these disks, I know that each of these disks are going to be on one of the pegs. So, for example, disk number 1 could be on peg 1, 2, or 3. What about disk number 2? Well, at any given time, disk number 2 could also be on peg 1, 2, or 3. Same thing with disk number 3, 1, 2, or 3. And finally, the very last disk could also have 3 options for which peg it could possibly be on. And so what we can do is to figure out the total size of the state space, we can multiply together these 3 possibilities that we have for where disk number 1 could be, so which of these 3 pegs, times the number of places that disk number 2 could be, number of places disk number 3 could be, and so on and so forth, all the way down to the number of places that disk number n could be on. And when you multiply all this out, this will just be 3 to the n. And that's going to be the size of our state space. What's the start state? Well, we actually already kind of talked about this when we were thinking about a state space representation. the start state is exactly going to be a representation where peg 1 has disk 1, 2, 3, 4 in this order. Peg 2 has nothing on it, and peg 3 also has nothing on it. So that's going to be our start state. All right, from a given state, what actions are legal? Well, we know that when we look at this example up here, we're always going to take the topmost disk from one of these pegs and move it over to another peg. So that's one of the actions we can take. Now, are there any prohibited moves? Well, we can see here that we're never allowed to move a larger disk on top of a smaller disk. And so that means that essentially from any given state, what actions are legal? We can remove a disk from the top of a peg and place it on top of another peg if the topmost disk is always larger than the disk we are placing on top. What about our goal test? How can we check a condition that we have achieved our goal? Well, if you remember what our goal configuration was, if we had these 3 pegs, we wanted to have disk 4 at the very bottom, disk 3 above it, 2 and 1 stacked on like this. And so all we need to do is convert this pictorial representation into a state space representation that we can essentially just ask, is the current state of my game equal to this desired state? And so the state space representation for this picture is I have no disks on peg 1, no disks on peg 2, and I have the list of disks 1, 2, 3, 4 ordered as such on the finalmost peg. And so all we need to do is we need to just say check if state is equal to goal state, where the goal state is described like this. All right, let's talk about search and heuristics. In this example, we have a car-like agent, and you can see that visualized here. And the car-like agent is going to try to exit a maze. And this maze here has walls, and it has the goal state represented by this X. That's the final place that we want to get to exit the maze. Now our problem here says that the agent is directional, and it can always face one of 4 directions, north, south, east, west. A single action, the agent can either move forward at an adjustable velocity, or it can turn. The turning actions are left and right, which change the agent's direction by 90 degrees. And that, again, is going to change which direction it's going to be facing. And turning is only permitted when the velocity is 0, and the moving actions are fast and slow. If you apply a fast action, it increments the velocity by 1. If you take a slow action, it's going to decrement the velocity by 1. Any action that's going to reduce v below 0 or above a maximum speed limit Vmax is also illegal. And the agent's goal is to find a plan which parks it stationary at the exit square using as few actions, which in this case corresponds to time steps, as possible. If our grid is m by n, the first question asks us, what is the size of this state space? So let's copy over this image here to keep with us down here and think about what our state space is. So we know that there are m by n xy positions that our agent could be in. So we know that part of the state space size is going to be all m by n coordinates where the agent could be. But in our problem, we also know that the directionality matters, whether or not the agent is facing north, south, east, or west. And so we're going to multiply this number by 4, where 4 corresponds to all of these 4 possible directions that our agent could be facing: north, south, east, and west. Finally, what other piece of information matters for us when we are, for example, applying an action or asking ourselves, are we at the goal? Well, we know that at the goal, when we want to exit the maze, we want to have a velocity of 0. And so this is going to tell us that we need to somehow be able to query about the state of our car-like agent and say, hey, do you have a velocity of 0? And so what this tells us is that velocity, or the number of possible velocities that our agent could take, is also something that we should encode inside of our state space. So this means that we should ask ourselves, how many possible velocities might there be? Well, if you think about it, we can be at velocity 0, 1, 2, all the way up to V max. Now, what's the total number of velocities here? Well, it's just going to be V max plus 1. And so we're going to multiply that number together by the prior quantities of states that we've already encoded, and this will be the total size of our state space. Next question, is the Manhattan distance from the agent's location to the exit's location admissible? Why or why not? Now, so far in a lot of the lectures and the projects, we've seen a Pac-Man type of world. And in a Pac-Man's agent kind of world, in that case, Manhattan distance was admissible. But let's think about if that's admissible now for this agent that gets to accelerate and decelerate, change its velocity. And in fact, the way we're going to think about this is, let's think about a little example here. So let's imagine that our agent is in this maze, that's actually just a singular hallway. It's a really simple maze. And it's trying to get over here to the very far right of the maze. And it's going to start out at the 0th position in the maze. So at time equals 0, the agent has 0 velocity and is faced east. Okay, so let's think through what's the fastest way that our agent could ever get to the rightmost goal, which is marked as an X. Well, I could immediately apply the fast action. Okay, so fast will move my agent here. It's going to say t equals 1, v equals 1. Next thing, what should we do? Let's increment again. Let's say our agent is once again accelerating. Now, at time equals 2, our velocity is going to be 2 as well. One thing I should have mentioned is in this little example, for the sake of argument here, I'm going to say that our Vmax is going to equal 3. Okay, so we're not yet at Vmax, so we can accelerate one more time. Let's try to do that. So we're going to apply fast one more time. Now, where is our agent going to end up? They're going to end up at state 6 at time equals 3 with a velocity of 3. Let's start slowing down so we can actually reach the goal. So we're going to take a slow action. This is going to land our agent at t equals 4 with a v equals 2. Let's slow down one more time. This is going to land our agent at the final state, t equals 5, v equals 1, but we're not yet stopped. So we're going to take one more action to slow down. At t equals 6, we will have finally achieved a v equals 0 at our final destination. Now, if we think about the total time it took us to go from the start to the goal, the time that it took us was 6 time steps, right? What would Manhattan distance say? Well, Manhattan distance would say, oh, it's going to take you essentially 9 steps to go from the start to the goal. So Manhattan would say 9. Now we ask ourselves, would Manhattan distance be an admissible heuristic? To figure this out, let's remind ourselves what an admissible heuristic even is. So an admissible heuristic is one that never overestimates the cost to goal. So in mathematical terms here, for some heuristic h, and if you're evaluating a node n, that heuristic will always under-approximate the true cost to the goal. So that means that if, in our example, it actually took us 6 time steps to get to the goal, For Manhattan distance to be admissible, it needs to be less than or equal to 6. Unfortunately, we see that 9 is greater than or equal to 6, and so this means that Manhattan distance is not admissible because it's overestimating the cost to the goal. Okay, let's take a look at the next question. Next question says, state and justify a non-trivial admissible heuristic for the problem, which is not the Manhattan distance to the exit. Okay, there's several different kind of answers we could come up with for this. So let's start out with maybe the simplest possible idea. The simplest possible idea would be to maybe choose a heuristic, h of n, which is just equal to, let's say, the number of turns the agent takes to face the goal. This heuristic will always under-approximate the total time it takes to get to the goal. So this one's admissible. Can we do a little bit better? Well, another thing we could do is we could choose h of n to be equal to d Manhattan, so the total Manhattan distance, where we essentially now are ignoring walls. We're going to assume that our agent can instantaneously turn and instantaneously achieve some desired velocity and just hold it there. So now our agent is a lot more flexible than the actual agent is in our problem. This is called a relaxation of the full problem. And so what we're going to say is this Manhattan distance, which just lets our agent instantaneously reach some desired max velocity, hold it there, ignore all the walls, and get to the goal. But to make it under-approximate the true time, because we already know that full Manhattan distance over-approximates it, let's scale the Manhattan distance by the max velocity. And so intuitively, let's think back to our earlier example. Remember how we had this world, this hallway world, where our agent just goes from 0 to 9? Well, we knew that d Manhattan equals 9, and we knew that our v max equaled 3. Well, if we look at this heuristic, so h of n here, we'll take 9, which 9 is a distance length. So it's something, you can think of it as like meters, for example. And v max is a velocity. So it's something like, meters per second. If you divide this, this gives us 3 seconds. Now, is 3 seconds an under approximation of the total 6 seconds that it took us to get to the goal? Yes. And so this is an admissible heuristic. Can we do even better? Well, let's think about maybe the most complex admissible heuristic that could work for this problem. And for that, I'm going to go to a sort of new sheet of paper here for us to write some more details on. All right, so option number 3. So can we improve upon this heuristic that says d Manhattan over v max? Okay, so let's think about what's one step closer towards modeling the true problem, but still keeping it a relaxation of the entire true problem that we're trying to solve. Well, so far all we did was we assumed that there were no walls, that our agent could instantaneously accelerate and reach some desired velocity, hold it there, and then get to the goal. So what if we add back this need for our agent to accelerate and decelerate? That's going to help us take one step closer to modeling the exact dynamics of our real system, of our real car-like agent. And that will mean that our heuristic is a little bit more complex, a little bit closer to H star. So now what we want to do is we want to account for acceleration and deceleration. So let's think back to that example that we were talking about before. We have our agent facing like this. Here's our goal. This is the simplest, most environment. And what we can do now is, if we think about the overall Manhattan distance, d Manhattan, now that our agent has to accelerate and decelerate, we can divide this total distance into 3 segments. The first segment, let's call it d excel, which is the distance that our agent travels while it's still accelerating. Then the middle section here, let's call that dv max. That's going to be the total distance traveled by our agent when it's just maxing out its velocity. And then the final segment is going to be decel. That's going to be the distance that our agent travels as it's decelerating all the way down to v equals 0 when it reaches the goal. So based on this, we can write down an equation for what d Manhattan equals. So we can say that d Manhattan will equal dxl plus dv max plus decel. Okay, now can we actually come up with more explicit numbers, like more explicit formulas for what these distances, each of these three distances are? Well, let's look at dxl. So for dxl, intuitively what's happening there is our agent chooses to go fast, v equals 1, it gets to move a distance of 1. Then it accelerates again, d equals 2, it gets to move 2 squares. And it keeps doing this until it hits v max. So the total distance it's going to travel during this acceleration period is 1 plus 2 plus 3 all the way up to v max. We can simplify this expression a little bit and rewrite it as v max times v max plus 1 all the way over 2. What about decel? It's kind of the mirror image of this acceleration portion of our movement. Well, in deceleration, we're starting at that v max, but we're going to take a slow action. That's going to move us v max minus 1 distance. We're going to decelerate one more time. That's going to take us v max minus 2 distance. I want to keep slowing down until our agent reaches a velocity of 0. So written out in math, that's going to take us v max minus 1 distance plus v max minus 2 plus all the way down to 2, 1, 0. And this total expression can be rewritten again in a slightly simpler form as v max times v max minus 1 over 2. What about this middle section? So we've just figured out how to represent this early part and like figure out how far we travel in the later part of the trajectory. What about this middle segment, this dv max? How long are we going to spend there? Well, we can use this equation from earlier, and we can say that dv max will equal d Manhattan minus dxl minus decel. What's nice is we actually have expressions for dxl and decel. We just figured those out. So let's plug those in. We have d Manhattan minus v max plus 1 over 2 minus v max minus 1 over 2. If we do a little bit of algebra, cancel some stuff out, we can eventually find that d man minus v max squared is the final expression. So it's simplified down a lot. Okay, this is nice. So we now kind of have this representation of how far our agent's going to travel in these different parts of our trajectory. But if we think about what the heuristic is encoding, the heuristic's encoding this time it takes us to reach the goal, because that's our estimate of the cost of the goal. So what are the corresponding times or the number of steps that it takes us to travel each of these portions? So when we're talking about DXL, how much time did it take for us to traverse this distance? Well, it just took us V max. So number of time steps, V max. What about for the deceleration portion? What are the number of time steps here? It's actually the same, because we're also just going from our max acceleration or max velocity all the way down to 0. What about this final portion? What about the number of steps that it takes us to travel this V max distance? The number time steps here. Well, we can just take that length, this dv max, this distance we're going to be spending maxing out our velocity, and again, divide it by our max velocity to get that overall time. So we're just going to take d Manhattan minus v max squared over v max, just like we did in the prior heuristic. Okay, so if we think about what the total steps that our heuristic is going to use, we're going to use this estimate of the acceleration time, the Vmax time, plus the deceleration time. So now our total steps is going to be Vmax plus d Manhattan minus v max squared over v max plus v max, where each of these, remember, this guy comes from this acceleration portion, this guy comes from the v max portion, and this guy comes from the deceleration portion. Let's simplify some of these terms. And what we're going to end up getting is d Manhattan over v max plus v max. Okay, so we found one slightly more rich estimated cost to go when we're actually taking into account acceleration and deceleration. The last thing that we need to do is we actually need to think a little bit more about what our final heuristic is, because we need to think about the scenario that might arise here. So let's think about this equation right here that we use to solve for the distance traveled at max velocity. All right, so let's think about this equation that we had from before. So we use this equation that dv max equals d Manhattan minus v max squared. And this would be a fine equation, except we need to make sure whether or not this dv max is going to be a positive number or potentially a negative number or a zero, because that's going to tell us how long we're actually going to be traveling with this maxed out velocity. So to figure that out, let's think about two cases. We have case one, d Manhattan is greater than v max squared, and then case two is going to be d Manhattan is less than or equal to v max squared. If d Manhattan is greater than v max squared, then we know that the distance traveled when we're maxing out our velocity is going to be greater than zero. This is exactly that setup we were just talking about, where we knew there was going to be this portion where we're doing acceleration, a portion where we're doing deceleration, and some non-zero portion of our movement through the space where we're maxing out our velocity. And so we know that if we're in this case, then the heuristic that we just came up with, h of n, which equals to this under approximation of the total number of steps, is valid. But what about this other case? What if the Manhattan distance is less than v max squared? Well, in that case, we know that we're essentially not going to be spending any time maxing out our velocity. So that's essentially, think of this example here, where all we do is essentially spend some time de-acceleration and then immediately start decelerating. In this case, we can choose, we need to choose a different heuristic, and we can actually choose the old heuristic we found, which was our second admissible heuristic that we came up with, which still under approximates the cost to the goal and can exactly help us deal with this scenario. So now we've come up with the final heuristic for these two possible scenarios when we're actually taking into account that our agent gets to accelerate and decelerate. So putting that all together, we have that our final most complex but still admissible h of n is going to be D Manhattan over V max if D Manhattan is less than or equal to V max squared. And we have D Manhattan over V max plus V max if D Manhattan is greater than V max squared. Let's just align these up nice. And that's going to be our final heuristic for this problem. All right, let's take a step back here. So we finished this guy, and now we can move on to part D. So in part D, we are interested in answering the question, if we use an inadmissible heuristic in A-star graph search, would the search be complete? Would it be optimal? So in this case, if the inadmissible heuristic is bounded. So all that means here is that our heuristic is still greater than or equal to 0, but it's going to be less than or equal to some finite constant c, which is not equal to infinity. That's just all it means to be bounded. Then A star will be complete. Now, why is this? We can sort of think through this because we know that A star graph search eventually visits all of the nodes if this heuristic function is bounded. And that means that eventually it would find a path to the goal state if there exists one. An inadmissible heuristic does not guarantee this property. Now, what about optimality? Well, an inadmissible heuristic does not guarantee optimality because it can make a good optimal goal look as though it's very far off and take you to a suboptimal goal instead. So no, not optimal. And you can think about an example that we saw in lecture about why this might be the case. We had this state space graph where we had a heuristic, h equals 7 here, h equals 6 here, and h equals 0, with the actual edge costs being 1, 3, and 5. And this inadmissible heuristic falsely makes us makes our A star graph search choose this path, even though we know that it's actually higher cost because 5 is greater than 3 plus 1, which is 4, just because we had such a poor inadmissible heuristic. All right, part E. If we use an admissible heuristic in A star graph search, is it guaranteed to return an optimal solution? So we have, again, this notion of admissibility. We're talking about graph search, and we're asking, is it going to give us an optimal solution? Then the next part says, what if the heuristic was consistent? So before we answer this question, let's think about what consistency means versus admissibility. So let's go back up here. So we've already seen the definition of an admissible heuristic. What about a consistent heuristic? Well, a consistent heuristic always underestimates the arc cost that it takes to go from some node A to some node C. So here in math, if we have two nodes, A and C, if I query the heuristic at A, and then I query the heuristic at C, and I ask myself, what's the total arc cost between the two, I want that to be less than or equal to the true arc cost from A to C. And I want this to hold for all possible A, C node pairs in my state space graph. Now, if we go back to our problem, if we use an admissible heuristic in A star graph search, it is not guaranteed to return an optimal solution in graph search. However, if we were doing A star tree search, it would be. So admissibility guarantees optimality for A star tree search but not for graph search. For graph search, we need this notion of consistency to be actually able to find an optimal solution. So if heuristic is consistent, then A star graph search is optimal. Now, to get some intuition for this, if we can look back to actually an example from the lectures, where here we have a state space graph. You can see here each of the true edge costs, so like 1, 2, and 3, and then we have also the heuristic here. Now, this heuristic here is admissible, but not consistent. Why is it not consistent? Well, let's think about this example right here. If I'm doing that sanity check for consistency, what am I going to do? I'm going to say, well, what's the heuristic of A minus the heuristic of S? That's going to be 4 minus 2. And then I'm going to ask myself, what's the actual cost from from S to A equals 1. And we needed an underestimate. So consistency says that H of A minus H of C is less than or equal to the actual cost from A to C. Well, 2 is greater than 1, and so this is not consistent. However, you can sanity check that all of these heuristics do meet the admissibility criteria. Now, to see the difference between A star tree search and graph search and their ability to be optimal under the admissibility or consistency of a heuristic, we can look at the search tree that corresponds to the state space graph, where here we're gonna write down each of the nodes as well as their neighbors. And then on the right-hand side here, you see the cost to get to that node. So this is gonna be the cumulative cost or the backwards cost to get to that goal, to get to that node. And then the second part of this is going to be that heuristic cost, that heuristic estimate of the cost to go to the goal. So here we have the backwards cost, and here we have the forwards estimate. And so I've just written that out over time here. Now, because A star tree search doesn't keep a closed list, what's going to happen is that as you run A star tree search, it's going to be able to first visit this C, but then also revisit this node C later and find its way to this goal, which is the lowest cost path to the goal. Unfortunately, because A star graph search keeps that closed list, it's going to find its way first to this C node on the very right. And then because it's already visited that node, it's already pulled it off the fringe and expanded it, when it returns to try to evaluate this node C, which actually does lead it to a better, lower cost path to the goal, it won't be able to expand this node because C is already going to be in this closed set. And so ultimately what that leads to is, again, this idea that if we run tree search, then an admissible heuristic will give us optimality. But when we are running graph search and we're keeping track of this closed set, admissibility does not imply optimality, but consistency will. It will make sure that we actually do get to expand that C and find our way to the shortest path towards the goal. All right, last question. Give a general advantage that an inadmissible heuristic might have over an admissible one. Well, there are two factors that contribute to the time it takes to run A star. The first factor is going to be the number of nodes that are expanded. And the second is going to be the time spent per node. So how much compute time spent per node. This time spent per node is typically governed by our heuristic. So if we have a really easy to compute heuristic, it's going to take us a very short amount of time at any given node to compute that heuristic and evaluate it. And so one general advantage that an inadmissible heuristic might have over an admissible one is maybe that inadmissible heuristic is really fast to compute. And so in the scenarios where maybe you don't care as much about an optimal path, because an inadmissible heuristic will not give us optimality, but you want to have a really fast algorithm, that might be a trade-off that you might be interested in. So here, this inadmissible heuristic could be fast to compute, even if it gives a suboptimal answer. And so this is kind of a design choice here, where if you, in your particular problem domain, don't feel that having an optimal solution is really important, then it might be desirable for you to choose an inadmissible heuristic that's really, really efficient to compute to make your A* run really fast. And with that, we reached the end of discussion section 1. Thank you guys for joining.